Hey friends, so we're trying to understand when a linear transform can fit a training set. It's equivalent to solving a system of linear equations, except we're trying to understand it, I guess, like visually. Because I think like the general consensus on like a system of linear equations is solvable is like you compute the determinants or something. So we're just trying to understand, like in this specific case, if there's a way to better understand. So like the visualization, like it's what we have happening right now is we are sort of doing some sort of like kind of random walk in the solution space. So like these are all linear transforms that fit this specific 2-point or 2-element training set. And so kind of like our so the first I guess kind of like conjecture we have is that like all 2-element training sets are fittable. And then the thing we're trying to understand is that we know empirically that like not all 3-element training sets are fittable. And we're trying to kind of like develop this theory where it's like if like if I have a linear transform that is like, say, successfully fitting a particular 2-point training set, we want to say something that like the motions available to the linear transform. So by motion we mean any compound or single weight motion, weight alteration. They all produce motions. Although I have a problem with my user interface, which is why it's jumping around, but we're just going to completely ignore that. And so we're trying to say, like, if if I'm constrained, if my linear transform is currently constrained to fitting a specific 2-element training set, then the motions available to it in terms of like weight or like compound weight alterations is restricted. And so like if you can understand like the restrictions on like the motions that are available, then maybe it would be possible to say like if I add another training point, then like it would have, in order to fit that, you would have to engage some sort of motion, and like it's like we know that we don't have that motion, so therefore this training set is not fittable. So like that's like the general theory, or like the general like conceptual, and like it's not great, but like whatever. But what we're doing today is so like to understand like what's happening with the weights, right? We have them here, but we want to have like a graphical visualization. So like the like a line graph, whatever like whatever you would call it. So so we're gonna create a little canvas div for creating a weight trace. So like each weight is going to, like at each time step is going to have a point at its value, so you can like watch the weights go up and down and whatnot. And so we're going to have a canvas, and we're going to add it. Like I have this using like a grid layout, and it's not quite doing what I want it to do presently, because you know, like it looks weird. But yeah, we'll just ignore that anyway. So okay, so to implement the weight trace visualization, I think, you know, so like we have a animation step at every time step, and so I think the main problem, well, yeah, I mean the main problem is that you know, the weights can kind of scale well, yeah, so it's like do I want to handle the scaling? I don't yeah, I think I'll just ignore scaling for now. So like the y-axis will just be a solid like -4 to +4, and then however many pixels you can fit in there depending on how large we make the canvas. And then the only other thing you really have to handle is when you go off screen, like the scrolling, which means like you'd have to have like a history. Yeah, I guess we could have like a weight history, and then at every time step we just redraw the history, which is well, yeah, I mean there's only 6 weights, so that's fine. Okay, so we'll do that. So we'll have a weight history, and oh yeah, I need like a div. I need to create a div. Yeah, I'm gonna delete all this. This was from a prior. That was kind of cool, though, I should say. Should I create like a new file? Cause we're kind of doing nah. Okay, so yeah, all right. Okay, so so first we're going to create the div, or well, it's gonna be a canvas. So and I'm using like GitHub Copilot, and it helps us. So you create a canvas for visualizing the weights of the neural net over time, right? Yeah, so we're gonna call this weight trace. And oh, it wants us to put it in row 1 to 2. No, that's not gonna work. Grid column, width, height. Well, it's a canvas, so I think you need to it really likes CSS, but you need to set its width. Don't you need to explicitly set the width of a okay, so okay, so where are we gonna put it? We're gonna put it oops. So wow, this is kind of hard to see. No, sure, no. Okay, so yeah, okay, so that's column. So we want it to be in row 2. Well, do I need like another row? How many rows do, display grid, auto rows. Oh. Yeah. Okay, that's fine. We'll put it on the right side for now. It's not going to look all that great, but that's fine, because that gives us more room. So it's going to go from columns 3 to 6 and row 2. Okay, so let's say 3 to 6 in row 2. And then the width can be, like, this is 400, so maybe like 600? Yeah, let's say like 600 pixels. And the height, maybe like 400. And so then we can just directly add that. Does this work for a canvas? Because that'll make it white. But that's kind of what I want, because I want to be able to see it. Okay, so it's now in our canvas. Oh my goodness. Yeah, it's too high. Go down to like 300. Whoa. 200. Yeah, that's better. So yeah, this is like from an aesthetic layout perspective, this looks like garbage, but that's fine. That's fine. Yeah, and then we can like set the background color to be not as bright. Hopefully. Yeah. Okay. And I think I'm going to ignore putting a axis, because like you can see the weights right here, so like we don't need a separate axis. So yeah, so yeah, so every time step we're going to, well, I actually don't have a lot happening in my animation thing. That's cool though. So we will now update the, whoa, it knew. See, this is the thing that kind of creeps me out, because you know, it's kind of like if you can write a comment and then it writes code, and you're like, yeah, I could see that, but this is like predicting the comments I'm gonna write. It's kind of it's too much. It's too much. Okay, so clear, yes, good. Begin path. No, this is not. What is it doing? Wait, trace. Yeah, I mean, the first thing we have to do though is we have to add the weights to the weight history, isn't it? Well, it depends if you want it to scroll. Do I want it to scroll or just overwrite like an oscilloscope? We'll just overwrite like an oscilloscope. Yeah. So we need weight trace y, and then yeah, then we're just gonna draw the weights. Also, we don't want to clear the rectangle though. So update the weight trace by drawing the weights array at the current weight trace y position. Yeah, except it's actually x, because it's an x. Whoops. Okay. Each weight is drawn as a, yeah, with a 1 pixel with its own color. I think I have like a color palette somewhere. Is this like globally scoped? No, that's not globally scoped. Well, I will make it globally scoped. Okay. Now it's globally scoped. Okay, then I need to refine my function here, and then yeah, okay. So it should have a better no, we don't clear the rectangle. Gonna have to comment that out. Color, fill style, fill rectangle at X. Fill right now. Wow, it's not even doing what it said it would do. So the color needs to be palette I, and then fill rectangle at weights I. We need to normalize weights. I think that puts it between -1 and 1, but weights I, and then times weight width. And then update the +1, but we need to mod it. +1 mod weight trace the width. Okay, so that should be totally cool. Let's find out. Yeah. Something broke. Something broke. So I need like my console. Weight trace is not defined at 720. Oh, I forget it. Oh. Tricky, there's 2 T's right next to each other. That'll do you in. The old 2T scenario. Oh yeah, I forgot to turn off clear rectangle. Don't do that. Okay. Yeah, I think my normalize isn't doing what I thought it would do. Where did I define that? Oh, yeah. Do I have lerp? Right. Let's see if I can write this. Let's see. Like we wanted to go from that will normalize a value from a range, from a minimum. Is that how you spell minimum? Minimum to a maximum range to a value from 0 to 1. That's what we want, isn't it? Value minus the minimum over maximum minus the minimum. Is that right? We'll just pretend that it's right. Because otherwise, like, I'd have to think about it. So we want to say the value, and I want to say it's from -5 to +5. I think even -4. Okay. Yeah, it's not drawing anything. Yeah. So it's taking weights I and mapping it to 0, 1. This needs to be the height. Wow. And 0, 1. That should work. It's doing something. Oh, dang. Oh, also, this is like, I did that wrong too. Okay, it's doing something terribly. Okay, so I'm gonna have to just do a normal solve. Also, is this like stroke style or? Oh, also this needs to be okay, alright, I got all the stupid stuff taken care of, I think. Finally, it's different colors. Fill rectangle. Oh, that says 11. Yeah, that shouldn't say 11. I think they might need to be bigger, actually. Yeah. Well, I don't know. Oh, look at that. It's beautiful. Can I make it go quicker? Yeah, not really. Okay, so I'm gonna have to do an actual solve. And, hopefully. So we actually, instead of whatever it's doing right now, okay, we're gonna comment all this out, and we just wanted to do a solve. One solve, please. Okay, so this should be like super cool. Oh yeah, that is super cool. Alright, now, if I as a human perturb the weights, oh yeah, do I need to implement like a, because like the two of the weights are gonna jump, I would think. Oh, it found like a new steady attractor basin. You guys like attractor basins, don't you? Alright, so like that goes small, and then like that goes there. I'm manually manipulating weights. Whoa. Yeah, that is pretty cool, I'm not gonna lie. Not gonna lie. So, okay, let's see if it loops. It should do like an oscilloscope. Whoa, oh yeah, but I forgot to, yeah, you really need to draw the entire, column. Okay, so let's fix that. And, we need to draw an entire column. And it needs to be the background color. ctx stuff fill style equals, I think we have it at 155. And yeah, waitress from the top of this, why is this? The y value is 0 because it's right, and then the width is 1, and the heighteth is the height of the thing. Okay, so that should do the oscilloscope situation. Oh yeah, except we only did it once. Wow. Okay. Oh, yeah, and then like go faster and stuff. Whoa. Righto. Now I wonder if, okay, so let's like do the thing, then like add, like a new new weight, like say 27 has to map to 27. What's that gonna do? Whoa. It didn't really do anything. I think we can make this a little tighter. Okay, yeah, let's just play around with this. Also, my FPS, I want to be basically at 100. Yeah. Okay. Right. This is very cool. And also, you know, like some of the oscillation is, you know, because like we're using Adigrad with momentum. So I think like the momentum is producing oscillations, if you can believe that. So let's say like 22 goes to 86. And then adapt. Whoa! That really is the coolest thing I've ever seen. Right, this is the weird thing, right? Like this weight situation, it matches the same two weights that this weight situation matches, plus an extra one. What if we add another one? Now the next one, I do not believe it will be able to fit. So it's gonna do like crazy oscillations, man. Oh, the oscilloscope works. Yeah, so like it can't fit that. But like let's reset the weights and it can try again. Yeah. Now it found almost the same setting. Also, I'm going to tighten the thingy again. It's just a question of finding it in my 1,000-line code script here. I guess like you're supposed to use different files or whatever, but okay. So this one goes to here, this one goes to here. Why is that not? Okay, and although I feel like I should include the 0 line. So like that's, oh, these two are 1. Yeah, it is flipped upside down actually. Yeah, let me try to flip it back the right way. Yeah, you just need to add a subtraction here. Or can I just make the weights negative? That would flip it upside down, wouldn't it? There's too much math involved. So we should have like 2. Yeah, like yellow and red are the ones that are 1 at the beginning. And then there should be 4 other weights. Yeah. Okay, so say, we want to map, say, 72 to 72. Is that 6 weights? 1, 2, 3, 4, 5, 6? Yeah. So, this is so weird, right? I mean, like, these 5 lines are successfully fitting 3 points, whereas these lines are successfully fitting 2 points. So let's just try to fit like 1 point. And of course that didn't work. Oh man, my UI didn't work. Come on, UI. It worked that time. That doesn't make any sense. Oh no, it doesn't, because it's not removing it. Can I remove this one? Okay, that works. Yeah, I'm not sure why that. I'm not even gonna deal with that. Right, so like these weights are fitting, you know, like a single training point. And you know, let's like just move the training point. Say 94. Oh, that broke everything. Oh, that broke everything. Wow. I'm having UI problems. Yeah, I don't want to deal with UI. You know? Oops. 1.0, 1.0. Right. Okay. So this is what we got going on. And then we're just going to move one of these, the green one, and, you know, we'll just arbitrarily say like, hey, 46. Okay, then it's going to re-equilibrate. Whoa. Right, I mean, like, everything's the same almost. So, like, the red was unaffected, but the yellow one went crazy. But then, like, what if we try to fit it from the identity function weights? Is it going to find... It finds pretty much the same solution except for the yellow. I do need to make that affected too. So we want to fit a single... One, two, three, four, five. Two of the weights, like, oh, okay, yeah, like 2 of the weights are the same value. That's why they're not visually distinguishable. But, yeah, so, like, if we just change, like, a single, if it doesn't break. Okay, it didn't break. No, it did break. Yeah, I'm gonna have to deal with that later. Okay, so I want to do the thing where we're gonna animate being within the solution set. Because, like, there's multiple I think I can get rid of this and this. Okay, so this is going to be like a different animation, but it's going to fit this training set, and then it's kind of going to produce different solutions, so like different weight settings that mostly solve the training set. Although it's going to take a while to like populate the weight trace. I think if okay, I'm going to turn that down, but then I'm going to do 2 steps in between refixing the weight. Hopefully that'll go faster. Yeah, like it produces more variability. Yeah. Yeah, this is kind of too slow. Okay, I'm just gonna keep that at 1 and then just say like 20. And yeah, let's also just keep it where it's the identity function, like on this specific set. Right, so these are all linear transforms that map 17 to 17, mostly, and 42 to 42, mostly. And yeah, so the weight trace is being pretty ridiculous. I mean, like, yeah, I'm not getting anything out of that. I think let's do yeah, so like we're walking the solution weight space by manually perturbing one of the weights to the current solution and then fixing it at that perturbation. And I think yeah, I was gonna tween that actually. That is what I should do. But I'm probably not gonna do that this time. Okay, but so these should be smaller. Yeah, I think it's still too jumpy. Yeah, it needs to be like a tween. But I mean, you can kind of see like blue and yellow are kind of alternating. Pink and cyan are kind of alternating. Right, I mean the whole time like we're ostensibly maintaining this. It's the identity function for a training set of size 2. So like the red weight doesn't really want to move. Yeah, like the red and green weights. I mean that's kind of an observation right there. It's like red and green are kind of like fixed. The yellow and the blue were kind of close to each other. And then like the cyan and the light blue were kind of fixed. Then they kind of diverged. The yellow guy is like going anywhere. But green and red are fixed. That's weird. That's pretty weird. Also, I should point out, like, the training set color and this color are not related. Okay, that's a pretty cool trace, though. So I'm gonna try to make it go faster. I turn down the variance and train the neural net, and that's gonna make the this needs to like maybe go to 3 again, because they go pretty crazy. And I don't know, make this 15 just to go a little bit faster. Okay, here we go. I mean, it does appear to be like fitting this pretty well, doesn't it? I would say so. But this this weight trace there is a weird tendency for the weights to increase like in absolute value. No, like just in value. Which I don't know why that would be. Okay, so let's do like a single training point. If I can trick my UI to work correctly. No, it already broke. Wow. Oh my god, I thought this worked, but like it clearly does not work. Can I remove everything? No. Bang. Okay, we're fitting this training set, kind of. Oh yeah, I was gonna do one with one. Actually, well, yeah, or like one with 3. Right, I mean, like, it seems, it seems like it would be the case that if you have like a training set of size 3, like these weights are gonna be significantly more constrained, although like it's not clear like in what ways exactly. Right, I mean I am noticing that like the yellow and the green weight are mirror images of one another. Don't know why. Actually, red and blue are too. That kind of makes me think I have a bug, because there's no reason why they would be mirror images of one another. Okay, so let's do like training sets of size 3. And first of all, let's see if it solves. Okay, this one, is it gonna solve it? Yeah, this one's kind of hard, because yeah, I'm not sure it's gonna solve that. Let's do like an easier one. Okay, so it's kind of solved it. Now it should be like, there might basically be only one solution, which means that the weights, you know, should not really move around that much. Which kind of looks like what's happening so far, right? Like the weights are much more constrained. Also, yellow and red are not... I'm trying to see if any of them are like mirror images of each other, which means there's a bug. I'm not seeing that though. So yeah, I think it's the case, like if there's basically only one solution for this training, because I think just training sets of size 3 in general either have no solution or one solution. Because I mean, like ultimately we have 6 weights, so you have 6 unknowns, and each training element gives you 2 equations for the x and the y value. So when you have a training set of size 3, you have 6 unknowns and 6 linear equations, which I think implies no, I don't know what it implies. Yeah, I forgot linear algebra, so... Well, no, it's like any linear system has either no solution, one solution, or infinitely many solutions. Isn't that... So maybe this one has just one solution? I don't know. Yeah, so it's all the weights are... so this kind of confirms that conjecture. Let's just try it on another training set of size 3. If it's gonna solve it. Yeah, it's kind of solving it. And yeah, I would say the weights appear to have stabilized. Kind of. Yeah, I would say it's pretty much... So, let's do another one, size 3. That one is, I think this is easy to solve, kind of. Yeah, like when you have to pull apart like close points, you're gonna get like huge weights. Yeah, like the yellow is already off the charts. And the green, so I'm gonna just get rid of that one. This one shouldn't be too bad. Yeah. Oh yeah, did that easy. And yeah, looks like the weights are gonna be pretty stable. So, let's go to the most unconstrained case, which would be training set of size 1, and see if we can see like a visual, like we can see a visual difference in the weight trace between training set of size 3 and training set of size 2, because like you're more constrained with 3, so the weights are pretty much lines. Whereas in the training set of size 2 case, it's less clear what the what's going on, but there was more freedom. And so let's look at the training set of size 1 case. So we have a single training set, easy to solve, and you can see like everything's going crazy. There's also like another problem is that like this method is not, I don't think, like uniformly sampling solutions. I mean, it just doesn't appear to be. So that's kind of a thing. But it's kind of like, like, could you distinguish in any way like this weight trace from, like just 6 independent random walks? Because it's not I mean, they kind of are independent random walks, except, they all have to map this. Add another point here for fun. So we added a second point right here. Is it going to look visually different? I mean, maybe, like it does seem like you have like the lines seem to follow each other more now, inexplicably. Okay, well, yeah. So we successfully implemented a wait trace.